And another important example, well, it's more of a construction. So if C is a DG category, we can define HC. I would like to call it the homotopy category of C, but that term is already reserved, but it's very closely related to it. The objects are the objects of C, and the morphisms in HC from an object X to an object Y of degree n. This is the nth cohomology of the cochain complex of morphisms between X and Y in the category C, meaning that it is sort of the kernel of the differential operator from the morphisms of degree n between X and Y to the morphisms of degree n plus 1 between X and Y divided by the image of the differential operator from n minus 1 to n between X and Y respectively. We define this as the morphisms, then the composition comes from D. It survives the quotient precisely because our differential operator obeys this Leibniz rule-like law. So the composition is well defined. And lastly, we take the differential to just be 0, because now we've taken cohomology, we've divided out all of that superfluous stuff, so now we just have 0. And one can show that with this definition, this is again a DG category. And now, two important applications of this cohomology category, whatever. If we take C to be the DG algebra that is the singular cochain complex. So for C being the one object category associated with the singular cochain complex, we get HC, well, is again the one object category associated with, well, a graded ring called the cohomology ring. And that one is called H bullet of X with coefficients in K, the singular cohomology ring or algebra or whatever. And another important example is, well, it's sort of half of an example, the category of R modules, where R is some K algebra. The objects are, well, R modules. But instead of taking the morphisms between X and Y to just be R modules, well, we need some sort of grading. So we're going to actually do a bit more. We're going to define this to be xn between X and Y over the ring R. In particular, if we take n to be 0, then we have x0, which is just the common R linear maps between X and Y. But for non-zero degrees, we get something interesting there. And the idea is that we can define xn to actually be the morphisms in the cohomology category of the category of complexes of R modules of degree n between, well, now we can't take X and Y, we take instead a projective resolution of X and a projective resolution of Y. Or injective resolutions, or whatever you want. And if we define it that way, there is a natural composition operation which, together with the definition of D equals 0, makes R mod into a DG category. And this is sort of a definition that motivates the whole idea of DG categories from the algebraic side. And as a last important example, which is sort of similar to this one, except now we're again dealing with differential geometry. For C, the one object category associated to omega of some manifold, we have HC, well again being a one object category, associated to some DG algebra, and that DG algebra now turns out to be the de Rham cohomology algebra. The de Rham algebra of M, where Hn de Rham of M is just the quotient of, well, by definition, it's the kernel of dn divided by the image of dn minus 1, or in other words, it is the closed n forms divided by the exact n forms. So this shows that the de Rham cohomology is also a DG algebra.